So continuing where we left off last time, we finished the day really starting to describe what's known as hybridization, which is a way of explaining this localized electron bonding model and how we get that out of the orbitals that we have. And so rather than having these pure atomic orbitals, what we wind up with are taking, we have to take these, the pure atomic orbitals of the hydrogen atom and combine them in ways that will give us new wave functions that describe orbitals that have shapes and orientations that really mimic the shapes of and the geometries of the electrons and the molecules that we looked at with VSEPR theory. So we started out looking at a very simple one, which was the beryllium dihydride or beryllium difluoride, and how in order for that molecule to exist, we need the beryllium itself to have orbitals that are oriented in a way that is linear. And the way we get that is we can combine the s orbital and the p orbital on the beryllium to give us two sp hybrid orbitals, and those sp hybrid orbitals are available basically to form bonds with surrounding atoms like fluorides, fluorines, or hydrogens. Okay. And so that's really sort of the thrust of this, is that we're taking these pure atomic wave functions and we're combining them in ways to get out these new hybrid atomic wave functions on the central atom as a way of modeling the molecule shapes that we know. And so the next step is to model the next type of shape, which would be something that would have a steric number of 3. And so in order to have a steric number of 3, you need to have, if we remember right, the electron geometry for steric number 3 is trigonal planar. So if we have something that's trigonal planar, in order to get that trigonal planar shape, we're going to combine an s orbital, right, the 2s, a 2p, and another 2p. Now, the subscript there, the pz or px, is somewhat arbitrary, depends upon how you frame your Cartesian coordinate system. But as long as you have 2 of the different p orbitals, so like a 2px and 2py, or 2pz and a 2px, that's going to be sufficient. And when you put those 3 orbitals together, the 2s, the 2px, and the 2pz, you wind up getting 3 hybrid sp2 atomic orbitals. And so here's what one of those orbitals is. Now these are all superimposed on, right, on the nucleus right in the middle, right? And so you could say, well, one of those lobes is in one shade and the other lobe is in the other shade. And of course we've got the 2 other ones. And so the other hybrid orbital, so here's another one. Right, and so there's one of the other hybrid orbitals, and then the third hybrid orbital, right, is right here. And so we put in 3 orbitals and we get out 3 orbitals based on the way that we combine the wave functions, right? We're combining functions, not just values. So we have to take into account all of the different phases. Of course, that means you have 3 sp2 hybrid orbitals, right? And you have 1 remaining unhybridized p orbital. Right, so that would be in this case the 2py orbital. Okay, and so the way that this helps us to get the shape is that if you look at the orbitals, right, if you look at these 3 orbitals, they're oriented in such a way as to have 120-degree angles between those orbitals, which helps us to explain the trigonal planar electron geometry. And so to look at this, we could, as an example of a molecule that would have this electron geometry, would be the boron trifluoride, right? Remember, boron forms the molecules in such a way as to have an incomplete octet, and that's fine. And so in order to form this particular structure, we have the boron. If we draw the Lewis structure, right, our boron would look trifluoride would look something like this. Right, and so we can get the steric number, right, steric number of 3 out of this, right? It's the total number of bonded atoms plus the total number of lone pair electrons on that central atom. And so when we have that, we can find that based on our Lewis structure, we can determine the steric number is 3. Grew over my electrons there. We can determine that steric number is 3. And then we know, if we know that the steric number of 3, we have a steric number of 3, then we know that the hybridization of the central atom is going to be sp2. Okay, and then when it comes to forming the molecule here, right, the boron sp2 hybrid orbital here, right, which is oriented toward the p orbital from a fluorine, right, that's going to be as those fluorines move in, if you will. If you put those fluorine atoms closer to the boron, you start to overlap those orbitals, right? You'll get a bond between the fluorine and the boron, such that you can share a pair of electrons in the overlap region of electron density, okay? And so that's sort of a key to this, right, is making sure that when you have a trigonal planar molecule, it's got the sp2 hybridization, right? The sp2 hybridization comes about, and we invoke this idea of hybridization as a way of modeling the shape that we see with for example, boron trifluoride molecule. Another example could be, say, boron trihydride, right? A little simpler molecule. So if you draw out the Lewis structure, and hopefully Lewis structure is getting easier as you're working on that lab. So you know that there's a steric number of 3. The electron geometry is trigonal planar, right? And so it's going to have sp2 hybridization. And so when you think about that, just as if you want to depict the orbital picture of this, right? So we've got a couple of things, right? We've got a Lewis structure. You can take the Lewis structure and do a perspective drawing. Right, so the perspective drawing would just be the boron in the middle with the hydrogens splayed out at 120-degree bond angles. Right, and then you could do an orbital picture of this, and the orbital picture would look something like this. You have the boron with 3 of these sp2 hybrid orbitals with hydrogens, and they're 1s. So coming from the boron is sp2 orbitals. You got 3 of them, right? sp2, sp2, and the hydrogen has a 1s. Another hydrogen has another 1s. Another hydrogen has another 1s. Okay. And they're going to share electrons in those overlapped regions. Okay. All right, so that would be an orbital picture of how the orbitals overlap to make this boron trihydride. Okay. Now, when we look at these bonds, just from that Lewis structure, right, we should be able to look at this Lewis structure, and because we can get all of this really useful information out, we should be able to describe that bond there as being, one thing is a sigma bond, and the sigma bond, remember, comes about where if you were to draw an axis, right, between the bonded atoms, right, so if you're just to draw a line between those bonded atoms, the nuclei, the hydrogen and the boron in this case, right, that would be one of our bonding axes. We'd have another bonding axis here and another bonding axis here. And so when you have those 3 bonding axes, you can take each of those sort of one at a time, if you will, right? And when you take them one at a time, the overlap of the orbitals occurs such that the orbitals overlap on that bonding axis, okay? And so that's how we know it's sigma bond. So that's how you know it's a sigma bond. So, come on, pen. There we go. So if I were to describe this bond here, right, I would know one thing, it's a sigma bond. And I would also know that the sigma bond comes about from the bonding of a boron sp2 orbital bonded to a hydrogen 1s orbital, okay? And so that's how I would get that sigma bond. And I can describe it sort of in that way as showing the orbitals that are coming from each of those atoms to overlap. And that's going to be important as you start to go down the path of reaction chemistry, where you're interested in how does a reaction proceed based on how the orbitals of the various reactants interact with each other. So that's our sp2 hybridization. We're going to come back and we're going to touch more on sp2 hybridization also when we start to look at double bonds. But we haven't started looking at double bonds and what pi bonds are. Jennifer, question.
Oh yes, I have a question. I'm kind of confused. So this is the electron geometry.
Mm-hmm.
So this will be different from the molecular shape.
Right. So the electron geometry describes all of the groups of electrons. So those can be bonds, so like a single bond, a double bond, or a triple bond. Those each count as one group of electrons, but it also takes into account the lone pairs. A lone pair is another group of electrons. But when it comes to the molecule shape doesn't include the lone pair in it, even though that lone pair influences where those other atoms are.
Can you repeat that, please?
Yeah, so when you take a molecule shape, right, and this is something to spend a little bit more time with at the end of chapter 8 stuff with VSEPR theory. But the molecule shape, right, is going to have a label that's describing where the atoms themselves are. And so even though a lone pair of electrons influences where the atoms are, it's not included in the shape of the molecule. The lone pair of electrons is, however, included in the electron geometry. Okay? And you can always come in and talk with me in office hours to expand on that a little bit too and get some more help on that. Yeah.
Thank you.
Okay, so there's our description of the sp2 hybridization. Again, there will be sp2 hybridization available when we have double bonds, and we'll talk about that once we describe the bonding in things that have double bonds. We haven't gotten to that point just. All right. So sp3 hybridization, I think this is one of the clearest examples of why we can't just describe things that are tetrahedral. And we know they're tetrahedral based on experiment. We can do things that are called, an experiment that's called X-ray crystallography. You can make an X-ray crystal structure to actually look at the structure of these molecules and how the atoms are oriented with respect to each other. But the hydrogen atomic orbitals don't do a good job of explaining how we get those shapes. And so again, we're modeling the shape of something that's tetrahedral or has a tetrahedral electron geometry. And we know that it has that because we're going to have anything with a steric number of 4. I have a tetrahedral electron geometry. And if it has a tetrahedral electron geometry, it's going to be sp3 hybrid. And an sp3 hybridized central atom, we construct the model for the wave functions of the orbitals on that central atom by combining the 2s, the 2p, and the 2p, so 3 of the 2p orbitals, the 2pz, the 2px, and the 2py, for something like hydrogen that is in the second period where its valence shell is 2. So it's for carbon, excuse me, that's in the second period, right? Its valence orbitals are the 2s and then the 2p orbitals. And so in order to explain the bonding in something like carbon as being a tetrahedral molecule in a molecule like say, methane, right? So CH4, right, which has a Lewis structure like this, right? But it's perspective drawing, right? We have to use the wedges and dashes to do that, right? Right, so if we do this perspective drawing, it shows something that's tetrahedral. And in order to get those tetrahedrally oriented orbitals, we have to invoke this idea of hybridization in our model. Okay, and so in this case, our orbitals are oriented in a tetrahedral shape. And I'm not going to draw over this structure other than to say that the overlay of the tetrahedron, I guess I'll draw lightly over it, right? The overlay of the tetrahedron here is meaning to show you that those the 4 sp3 hybrid orbitals are oriented in a way such that the orbitals are at the vertices of the tetrahedron. Yes, Maya.
Yes, I just have a question on trying to visualize the 3D model, like with using the wedge and the dash lines.
Mm-hmm.
So I was trying to look in the book, and do they show it a different way, or because I don't see any wedges or dashes?
They may not show it that way in this book. You have better artist renderings in most cases. You will see it in like all over the place in chemistry. So it's something you need to know even if it's not in this textbook.
Now, we'll be tested as well, drawing these with the wedges and the dashes as well? Okay.
Absolutely. Yeah, that's really important, especially if you're going on to organic chemistry. It's used a lot in organic chemistry.
Got it.
And so here we've got the shapes of the orbitals. Now, something I want to touch on, I'm going to go back and look at the sp2 hybridization in a second, is what happens to the energies of those orbitals when they become hybridized. So if you take and think about the energy of just the purely unhybridized atomic orbitals. So if we have a carbon atom with just pure atomic orbitals, right? You could look at the energy levels of those pure atomic orbitals as having just the valence orbitals, right? We're only going to look at the valence ones. Right? Those valence orbitals on the carbon are going to be the 2s, and then you have 3 2p orbitals. Try to raise that higher a little bit. You have 1, 2, 3, and those 2p orbitals are all the same height. When you have when you invoke this idea of hybridization to explain the shapes, so now you're going to have a carbon atom that's your central atom that is going to be sp3 hybrid. And if you look at the orbital energies of those, right, if you're taking all 4 of these orbitals over here and you're combining them to make sp3 hybrids, the overall energies of those, right, because we're talking about energy axes here, the overall energies of the resulting hybrid orbitals, they're all going to be the same energy. They're all the same shape and size, as you can see from the example down here. They're just different, oriented in different directions. And so what you're going to get is a set of 4 sp3 hybrid orbitals. They're all of the same energy. And of course, those are going to be the ones that are utilized to make a molecule like methane. If we go back up to here, I realize I didn't do this yet for the sp2 hybrid orbitals for, say, like a boron atom. If we do the same, I use that same idea here, right, and say, let's take a boron atom, right? So for something like BH3, so our central atom is that boron atom. And if we take and understand it as being the pure atomic orbitals, and I got to make sure I'm putting in electrons in here. Right, here's my 2s and my 1, 2, 3, 2p orbitals, and I should make sure I have my electrons. 1, 2, 3 electrons in the pure atomic orbitals of boron. Here, what I'm actually combining in order to make the boron atom in the molecule, which will be sp2 hybrid, right, what I'm combining is 2 of the p orbitals with the s orbital. So I'm taking 2 of those p orbitals now for an sp2 hybrid orbital, for the set of sp2 hybrid orbitals on the boron atom. I've got 1, 2, 3 sp2 orbitals, and left over that one, if you will, that one orbital there, and at the top that's left over is my leftover 2p orbital. Now I have 3 electrons that I can place in here. There's 1, 2, and 3. And those 3 electrons are in these sp2 hybrid orbitals that will combine with the bonded atoms to form the bonds with, say, the hydrogen around it. Okay, if I look at the carbon, if I think about a carbon atom, carbon has 1, 2, 3, 4 valence electrons. And so when I put those electrons into the sp3 hybrid carbons, each of those electrons will be in an orbital by itself, and those electrons are available for the bonding of the carbon atom to its surrounding atoms, for example, with methane. Okay? So here's an orbital picture of the methane molecule. And essentially, as these come together, you can imagine in each of these regions, you're sharing 2 electrons. One of those 2 electrons is coming from the carbon, and the other one is coming from the hydrogen. Okay. And so that gives you the orbital picture. This orbital picture is what allows us to have that 109.5 degree bond angle and the tetrahedral structure. Now keep in mind, remember, so I just did those energy diagrams, and again, I want to bring up the idea of the box diagrams or orbital like diagrams that we did when we did electron configurations, right? So the lab that you're going to be doing tomorrow is the VSEPR lab, and that one deals with these orbitals involved here, in particular the valence orbitals. So if you look at the valence orbitals for carbon, we have 2s. So they use circles, and I mentioned this yesterday, right? They use circles in that particular lab, right? The circles are all attached if they're the same energy, so 2s and the 2p. Carbon has, if you see the unhybridized carbon atom, right, it'll have its valence shell is the 2s and the 2p orbitals, right? But if that carbon atom is hybridized, what you wind up with, right, is going to be sp3 hybrid. All 4 of those orbitals are going to be sp3 hybrids. And so this is kind of showing you the picture of the carbon atom in its hybridized state, right? In the same way that we did the box diagrams back in chapter 7 for the electron configurations, okay? And so this is meant to give us a picture of both the shapes and orientations of the orbitals that are resulting in the bonds, but also is showing you how the orbitals overlap and how electrons are shared. Okay. Now, if we were to have something like water, okay, and I want you to think about water from the standpoint, so this first example, H2O, right, is, if we think about it, right, our Lewis structure for water, right, we've got a Lewis structure that looks like this, right? That Lewis structure for water has 2 bonds and 2 lone pairs of electrons on the oxygen atom. The oxygen atom still has steric number 4, so it's still going to be sp3 hybridized. But if we look now at the oxygen atom with these energy diagrams, so that oxygen atom, if we look at the pure atomic orbitals, right, we've got, again, and we're still looking at the 2s. Oops, I should make sure I have my energy here to let you know. We're talking about the energy of the orbitals. So oxygen has, so 2s and 2p orbitals, and it has a total of 6 valence electrons. So 1, 2, 3, 4, 5, 6. Okay. But if this is a an sp3 hybrid carbon because it's a steric, sp3 hybrid oxygen because it's steric number 4, and it's got an electron geometry that's tetrahedral, then you can take those orbitals and combine them and say, okay, we're going to make this sp3 hybridized oxygen atom. And that sp3 hybrid oxygen atom is going to have 4 sp3 orbitals to it. Okay, those orbitals will then be filled with the 6 valence electrons. So 1, 2, 3, 4, 5, 6. Well, that leaves two orbitals that have 1 electron in them and 2 orbitals that have 2. Now, if I think about the bonding in this molecule, each of the hydrogens is going to donate 1 electron to the bond between the oxygen and the hydrogen atoms. And the oxygen's going to provide the other electron in the bond. All right, so there's my bond, if you will, between the hydrogen and oxygen. But I've also got these 2 lone pairs of electrons, right? 2 orbitals of those sp3 orbitals each have a lone pair of electrons in them. So you can think about these as being lone pairs of electrons in those 2 sp3 hybrid orbitals, right? And those electrons in those sp3 hybrid orbitals are pushing, right, on the electrons in the bonds in our VSEPR theory. If we do the same thing for ammonia, right, we can look at the orbitals where we have an energy diagram for the ammonia atom, and it's pure atomic orbitals. Okay, and so for this, again, we're still talking about the second period, so 2s and 2p orbitals with a total of 5 valence electrons. So 2 in the 2s and 2 in the 2p. But if we look at the ammonia molecule has this tetrahedral electron geometry, right? It's a trigonal pyramidal shape. And so what happens here is those orbitals combine to give you sp3 hybrid nitrogen atom. And this sp3 hybrid nitrogen atom, you just fill it with the electrons. There's 5 valence electrons in nitrogen. And so you can look at the lone pair of electrons occupying the orbital up top, and each of these other orbitals having an electron from the nitrogen and 1 electron from the hydrogen. And so this is showing now how the electrons are overlapping and being shared. The orbitals are overlapping, the electrons are being shared in these molecules. It's also, we're able to depict now the energy of the orbitals once they're hybridized compared to the pure atomic orbitals from which they came. Okay. And so it's really important that you have this kind of a picture for anything that's sp hybridized, sp2 hybridized, or sp3 hybridized. When you start to look at molecules that are carbon-based, right, which is where you'll go if you go to organic chemistry, you see there are 4 elements that are primarily found in organic molecules. Now there's more than 4 total, but the 4 that you see the most often are carbon and hydrogen first, and then oxygen and nitrogen are 3rd and 4th. Okay, so of those organic compounds, you see a lot of carbon and hydrogen, and the carbon is going to be sp, sp2, or sp3 hybridized. So understanding how that works is important. Now, if we were to draw out an organic molecule like ethylene, ethane, we'll do ethane. So if I were to look at the molecule up top, this is C2H6, right? That would have a Lewis structure like this. And so if I were to look at the bonding here, right, I should be able to look at this Lewis structure and now be able to pick out what orbitals overlap to form that bond, and the type of bond that it is, right? Remember, we're talking about bonds that have that are symmetric on that bonding axis, so they're going to be sigma bonds. Okay, it's going to be a sigma bond that comes from the overlap of an sp2 orbital of the carbon and a 1s orbital from the hydrogen, and that any of those CH bonds in this particular molecule are all going to be equivalent. Okay. So that'll be a carbon sp, that should be, I should say sp3. There are 4 of those, sp3. So if there's a carbon sp3, right, there are 4 orbitals coming off, it's an sp3. Steric number's 4, you know it's sp3. Bonded to a hydrogen, 1s, and this is a slightly different way of depicting the orbitals involved in this, but this is sufficient also, saying it's a sigma bond forming between the carbon sp3 and the hydrogen 1s orbitals for any of those carbon-hydrogen bonds. We should be able to do the same thing for the carbon-carbon bond as well. So that carbon-carbon bond is forming from the sp3 of one carbon to the sp3 of another carbon. It's still a sigma bond because the orbitals overlap along the bonding axis there. And so it's a sigma bond coming from a carbon sp3 bonded to a carbon sp3 orbital, right? And so that's how you would identify the orbitals and the types of bonds in a molecule like methane, or like ethane, okay? And you could do that for any molecule as long as you understand that hybridization of the central atom. And in this case, we have 2 central atoms, right? We have 2 carbons that each have atoms bonded to them, surrounding them. And so you really have 2 central atoms that you need to take into account here. In our example below, right, this is a methanol molecule, so it's CH3OH. So if we have a Lewis structure of this, something like that. Now you've got 3 different types of bonds that you could identify. You have the carbon-hydrogen bond, right, which is a sigma bond, right? That's one of these. So sigma bond coming from the carbon sp3 orbital to the hydrogen 1s orbital. You have a carbon-oxygen bond, right, which is a sigma bond. That's this one here, coming from the carbon sp3 to the oxygen. Well, that oxygen also has 3 electron groups, right? It's got a steric number of 4. So it's also an oxygen sp3 orbital. And then you've got this oxygen carbon bond, which is going to be still a sigma bond, right? Still the orbitals overlap on that bonding axis. So it'll be a sigma bond coming from the oxygen sp3 to the hydrogen 1s orbital. Okay, so that's how we're identifying these bonds, and that's going to be important as you sort of proceed through organic chemistry in particular, but understanding how molecules are attached to each other. And when it comes to sp3d and sp3d2 hybridization, right, what we're looking at here, if you have a steric number of 5, you're going to have sp3d hybridization. And this one comes from, as you can see, the 3s orbital, 3 3p orbitals, and 1 3d orbital. And you can't have anything sp3d hybrid until you get to period 3, because you don't have d electrons until you get to period 3 on the periodic table. When it comes to sp3d2, that's going to have a steric number of 6. Right, and that one is coming from, again, the 3s orbital, if you have a period 3 atom, 3 3p orbitals, and 2 3d orbitals. So you'll notice that the number of electron groups, or the steric number, is going to equal the sum of the number of orbitals, right? 1 orbital coming from the 3s, 3 coming from the 3p, that gives you 4, and 2 more from the 3d gives you a steric number of 6. And so that's the hybridization of the molecules, or the central atoms of molecules that are have a steric number of 6, that are octahedral in their electron geometry. So you can sort of see from the table here, if we look at based on the steric number and hybridization, right? The trend here is that you have the steric number and hybridization and the sort of the orbital geometry or the electron geometry. Right? Those are all examples of molecules. We're given some examples of molecules that fall into this, right? And have those bond angles that we talked about in VSEPR theory. And you have some examples. You can see how the orbitals are oriented in this table. So this is kind of a good little summation table for getting molecules that have these ideal bond angles, right? Okay, now we're going to start talking a little bit about double bonds. Now, double bonds, if you remember our definition of a sigma bond, right? A sigma bond has electron density or overlap of the orbitals of bonded atoms along the bonding axis. So in this first picture up here, we can see sort of a sigma bonding framework, okay? In other words, if you were to take the molecule ethylene, okay? So ethylene is the molecule we're gonna look at. We're gonna start out with a Lewis structure. So this Lewis structure of ethylene, it's like so. Okay, so there's our Lewis structure of ethylene. We have 2 bonds, right? There are 2 bonds in there, right? It's a double bond. And so when we look at a double bond, we want to start looking at the orbital pictures here. We also know that carbon has a steric number of 3 for both carbons, right? And that's an important thing because that means that both carbons are going to be sp2 hybridized, right? And so if they're sp2 hybridized, we can develop as part of our sigma bonding framework, we can have these, each of those carbons can have these 3 sp2 orbitals coming away from them. And remember that the angles between those orbitals are going to be right on or around 120 degrees. So each carbon will have those 3 sp2 hybrid orbitals. Okay. Now for each carbon in this molecule, you can see that each carbon forms a single bond. Anytime you have a single bond, right? A single bond is going to be a sigma bond. Single equals sigma, okay? Because in that single bond, you're going to have overlap on that bonding axis. Now, that's not true in all cases, everywhere, all of the time. But for the level of chemistry that we're at, that single bond is going to be a sigma bond, okay? If you go on to inorganic chemistry, you'll see some weirder things that happen where you get single bonds that aren't. But here, for our intents and purposes, if it's a single bond, it's a sigma bond. Okay, and so each of the bonds that forms from the overlap of one of the hydrogen's 1s orbitals with an sp2 orbital from the carbon, right? That's going to give you, right, a sigma bond. Okay, in each of these cases, right? They're all going to be a bunch of sigma bonds. Okay. And on the other carbon also, right? You have 1s and an sp2, right? These are going to combine to give you sigma bonds, right? sp2 and 1s, right? The orbitals there are going to overlap to give you a sigma bond. Now, the first of the 2 bonds that we're going to describe with the carbon atoms is going to be the one in the middle, and that's going to be where you have overlap of an sp2 orbital from one carbon to the sp2 orbital of the other carbon. And those 2 orbitals are going to overlap to give you a sigma bond also. So the way to describe that, right, would be a sigma bond from carbon sp2 to carbon sp2, okay? And so that's a key here, is that we've got the orbital picture of the sigma framework in that first one. But if you remember from that, from what we talked about with sp2 hybrid orbitals, right? There's this 2p orbital that's not hybridized, right? This 2p orbital on each of those carbons is not hybridized. And if those two 2p orbitals on the carbon are not hybridized and they're in the same phase, then you can get, again, good overlap, right? And when you have good overlap between orbitals that are in the same phase, that can lead to a bond. So as these carbon atoms are brought closer together, so to speak, right, if you move them closer to each other, you start to get to a picture that looks more like this, up in the top right corner, where the overlap between these orbitals is sort of above and below the bonding axis, right, where the bonding axis is right there. That's what we're going to call a pi bond. Okay, so a pi bond, in this case, is forming from a carbon pure atomic 2p orbital to the carbon to, again, pure atomic 2p orbital. Okay, now you can specify which orbital it is, 2px, 2py, 2pz, doesn't really matter as long as they're the same, okay? But that's the orbital picture you get. And this is one orbital. This is an orbital. It just happens to be that this orbital has one phase up top, right? And the other, so there's my shaded phase, if you will, up top, and unshaded down at the bottom to give you one orbital. And so that's the second bond. So if you look at the bonding in a double bond consists of a single, the double bond consists of a sigma bond and a pi bond. Okay, that's a key here. And you should be able to describe the orbitals that overlap to give you those bonds in describing the bonding in the molecule, just like we did for the sigma bonds above, okay? And so that's what's going on. That's why these leftover orbitals that aren't hybridized are really important, is those orbitals that are unhybridized that are left over, they can also overlap to give an extra bond, right? So as to go from a single to a double bond. But the key here is if you have a single bond, that single bond has overlap on the bonding axis. The double bond has overlap above and below the bonding axis, okay? And it's sort of side to side overlap, if you will, right? These two p orbitals are coming in and they're overlapping side to side. The overlap of those orbitals is not really great compared to the overlap of the sigma orbitals. And so the extra bonding, if you remember back to when we were in chapter 8 and we looked at the bond enthalpies, the average bond enthalpies, we noticed we said that when you had a double bond, if you compared it to a similar single bond, so like a carbon-carbon double bond versus a carbon-carbon single bond, right? The double bond had bond enthalpy that was almost, the double bond was almost double the bond enthalpy of a single bond, but not quite. Part of that is just the orbital overlap is not quite as good when you have the p orbital overlap, right? So it'll be almost double, but not quite, okay? And so that's a double bond. And so if you were to look at the bonding in something like formaldehyde, so we looked at, where is it? Here, we looked at for sp2, right? This was methanol, right? Which is CH3OH. If we now look at the bonding in something like formaldehyde, which is CH2O, has a Lewis structure like this. Well, what you have here now is you have two single bonds that come from the overlap of the carbon, right, with the hydrogen. So there's the carbon sp2 hybrid orbitals. Again, they're sp2 because the steric number of carbon is 3. And then you've got that with the hydrogen atomic orbitals. So the overlap is the sp2 from the carbon and the 1s from the hydrogen. And then the carbon has this other sp2 hybrid orbital. And the oxygen has 3 sp2 hybrid orbitals. Okay. And so in the, for the oxygen, it has these sp2 hybrid orbitals, and there are 3 of them. You'll notice that if we look at the Lewis structure, you've got a couple of lone pairs of electrons. So those are going to reside in these orbitals over here, right? And you're going to get a bond there that's a sigma bond, where you get the overlap of the carbon sp2 hybrid orbital to the oxygen sp2 hybrid orbital. But you also have these 2p orbitals as well, right? And so these 2p orbitals, one there on the carbon and one there on the oxygen, right? If they're in the same phase, right, those 2p orbitals can combine to give you that double bond, where you have this sort of a side-to-side overlap again in this pi bond. So the pi bond, remember, is both of these areas, right? And they're just opposite phase of each other. This is the pi bond, though, right? And so you have a pi bond here that's formed from a carbon 2p orbital that's not hybridized. It's that pure atomic 2p orbital to the oxygen 2p orbital that's also not hybridized, okay? And so that's really showing in this case, notice how—
That should be pi bond, right? Not sigma.
Oh, sorry, yes, I think I said pi and I wrote sigma.
Yeah, you did.
Because I tell you, it takes a lot more brain power to do this on the computer right now for me compared to on a whiteboard. It's a lot harder. So thanks for fixing that one for me. Yeah, so that should be a pi bond that comes from the overlap of the 2p orbital. So again, the pi bonds are side-to-side overlap, okay? Okay, so there's an example in a very small molecule. Now, anytime you're given a Lewis structure, you should be able to identify what types of bonds, what types of orbitals are overlapping just from a Lewis structure, right? I should be able to go and say, hey, if I have this formaldehyde Lewis structure, right, I should be able to look at this and say, hey, each of those carbon-hydrogen bonds, right, each of those CH bonds, right, each of those are sigma bonds, and they come from the carbon sp2 bonded to a hydrogen 1s in each case, right? They're essentially the same type of bonds they're forming. And then if I look at the CO, right, this is a double bond here, so I can specify that, right? The CO double bond has a sigma bond and it has a pi bond. And so the sigma bond is represented from the overlap of the carbon sp2 orbital to the oxygen sp2 orbital. And the pi bond is coming from the carbon, that's not what I'm trying to do, carbon, not sigma. Come on, there we go. So carbon, 2p pure atomic orbital to the oxygen, 2p pure atomic orbital. So you should be able to describe these in each case, and that'll have significant importance when you get into an organic class. Now, when you have triple bonds, then—
Professor, I have a quick question. On an exam, is that how you would ask us a question? Like, if you would give us a formula and then say, you know, what is the hybridization for this structure?
Yeah, you should be able to sort of put it together like I just did. Really nice. And so what I think is important about this is being able to put it together in a straightforward way, noting that it's a sigma bond, and then saying the orbital from this atom is this orbital, the orbital from this other atom is this orbital. Yeah.
Okay. Thank you.
So when we think about triple bonds now it's important to start to put this in context of the molecule first. So if we think about this, we can look at acetylene. So acetylene has the chemical formula C2H2. And so you get a Lewis structure that looks like this. And so if you have C2H2, what you have is the carbon has a steric number of 2. And if we have steric number of 2, we know it has a linear electron geometry, right? Which means we have an sp hybrid carbon. So if we have sp hybrid, what that tells us is we have, off of each of these carbons here, we have these 2 sp hybrid orbitals. Okay. Now, if I take the left carbon first, and I can say, well, that sp hybrid orbital is going to be what forms the sigma bond with the H plus, with the hydrogen atom, right? And so that's going to come from our 1s from the hydrogen and the sp orbital from the carbon. And if I go to the one on the right, the one of the sp orbitals from the carbon on the right will overlap with the sp, or with the 1s orbital from the hydrogen on the right. So that's sp to 1s, right? And then I have this other sp hybrid orbital. Right, so this other sp hybrid orbital, back up here, from each of the carbons, and those are going to be the ones that overlap to give us the sigma bond for the triple bond. But when I have a triple bond, and so triple bonds have 1 sigma bond and 2 pi bonds. Okay, and the reason you can get 2 pi bonds is you have 2 p orbitals on each of those atoms. And so if one of my p orbitals on this carbon looks like that, and the one that's oriented in the same way in this case, this is a different molecule, this is HCN, but it's the neighboring atom. If those are oriented in the same way and in the same phase, then I can get overlap between these 2 p orbitals, 1 p orbital from each atom. And then if I have the p orbital on this other p orbital on each of those atoms, and they're in the same phase, I can get overlap between them. So this allows me to make now 2 pi orbitals, right? In the case of a triple bond, okay? So those 2 pi orbitals, so you have 1 pi orbital. So in the case of HCN, right, you have 1 sigma orbital, or excuse me, sigma bond, coming from the sp hybrid, or from the carbon, label that right. Okay. So the carbon sp hybrid orbital to the nitrogen sp hybrid orbital. And you know its nitrogen is sp hybrid because it has a steric number of 2 also, right? It has a lone pair of electrons and a triple bond, right? Then you have one of the pi orbitals is coming from a carbon 2p. Now, in general, if you're doing this, you should label these in many cases by picking one of the 2p orbitals that they're going to overlap. And since we want to sort of align our Cartesian coordinates for each of the central atoms here, we could say that's coming from the carbon 2px aligning with the nitrogen 2px, just to make sure that it's pictured in your head that we have the same Cartesian coordinate system at play for each of these atoms. Now it's arbitrary which one you pick, as long as they're the same, okay? So the other pi bond is from the carbon, let's say 2py, bonded to the nitrogen 2py, which would tell you that if you label those y and x for these 2 pi bonds, then the 2pz is part of the hybrid orbitals of the carbon, right? It would be the s orbital of carbon and the s and the 2py z orbital of the carbon. So just sort of, it's arbitrary which ones you pick as long as you're consistent, because we're trying to keep our Cartesian coordinate systems aligned. Okay, but that would describe the bonding in a molecule like HCN. At least this is the triple bond. The single bond, right, is still just going to be a sigma bond from the carbon sp to the hydrogen 1s. Okay. Now this has these single bonds and double bonds have and triple bonds have implications for what we can call the bond rotations. So when you have a single bond, so these single bonds come together, and so you can imagine the orbitals overlap, but they have symmetry on this bonding axis, so you can rotate the atoms, rotate the bond, if you will, and the atoms on the bonded atoms can spin as you rotate this bond. But as soon as you have a double bond and you have orbital overlap where you have the, if you will, you have the sigma bond, try to use different color pens here. So my sigma bond is in the middle, and that's overlap between those sp2 orbitals. And my double bond, right, has orbital overlap this way. There we go. Above and below. Now that orbital overlap above and below means that you can't rotate the bond. So it locks those molecule or those atoms in place, okay? And that will have implications, especially when you get into looking at organic molecules, for what are called isomers. They're basically molecules with the same chemical formula, but different structures. So as soon as you have a double bond, that molecule is locked in place, okay? And so you can't rotate it. Single bonds have the ability to rotate, right? Double bonds, you can't rotate them. And so that'll have implications for the molecule structure in the future. And when you have a triple bond, now you're looking at having, your sigma bond in the middle, right? Sigma bond's in the middle, and your pi bond is on the outside. You also have another pi bond coming sort of in and out of the plane of the board. So if you will, you got sigma bond in the middle, overlap of these two pi orbitals above and below that plane, but you also have it in this direction. So it still locks in place, but it's not going to have the same type of implications for structure that a double bond does, because the molecule is linear, and so the molecule itself sort of has this two-dimensional orbital type picture. Okay, and so if you look at acetylene, for example, if you take the pi bonds from acetylene, you can almost look at it as though it's got this electron distribution in a kind of a barrel shape all around the outside of that bonding axis, and that's where you get the pi bonds. Now, yeah, that's a way that you can look at it for electron densities. Okay, it's not entirely that simple, but it's one way to look at it. Okay. All right. So we've actually identified sigma and pi bonds, but one of the things I want us to do here is just pick out like a molecule, okay? And so I'm just gonna draw a molecule in here, and we're gonna identify some sigma and pi bonds in the molecule. Oop, what did I do there? That's not what I wanted to do. Sorry guys, it's taking me a second to draw this. There we go, that's what I want to do. And we won't identify every single bond in this molecule necessarily, but we'll look at some of the bonds for sure. You know what, yeah. Okay, so if we look at some of these bonds, one, we've got the CH bond. So that CH bond, okay, if it's a single bond, it's a sigma bond. So that's the first thing we can put down. We also know that the hydrogen is just going to have a 1s orbital. And we know that if we have the carbon has a steric number of 2, it's going to be sp hybrid, okay? Which means that the carbon has an sp orbital that's overlapping with the hydrogen 1s, okay? If we now take and look at the carbon-carbon triple bond, well, we know that our first carbon is sp hybrid. The second one has a steric number of 2 also, so it's also sp hybrid. Okay, so that's useful information. But if we have a triple bond, we already know we have a sigma bond and we have 2 pi bonds, and we can describe both of those pi bonds in this way. And so here we've got a carbon. For the sigma bond, it's a carbon sp orbital that's overlapping with the carbon sp orbital from the other carbon. And we know it's the sp orbitals because there's of how those sp orbitals are oriented toward each other. For one of the pi bonds, we're going to pick an axis and say, well, that's the carbon 2p, let's say x, and bonded to the other carbons 2px. And then for the second pi bond, we'll have a carbon 2p, and just arbitrarily pick either y or z. I'll pick y, bonded to the carbon 2py. So that's sort of what that tells you is if these are the x and y, the px and the py orbitals from the carbons, then the bonding axis is the z-axis. And so that's sort of a convention that a lot of chemists use, is saying the bonding axis is the z-axis. If we go on to our next bond, okay, that's a single bond. So this is a carbon-carbon single bond. And so this carbon-carbon single bond, well, if it's a single bond, it's a sigma bond. And I know that the first carbon that we've already looked at is sp hybridized. That second carbon is sp2 hybrid because it has a steric number of 3. And so what we have here is we have a carbon sp orbital from one of the carbons overlapping with a carbon sp2 orbital from the other one. Now, you don't have to specify, or you don't have to necessarily put one first or the other first, the sp or the sp2, but in general, if you have sort of a right to left on a picture, you should keep your identified carbons in the left and right side also. Okay. So we'll go to our next bond here, which is the carbon hydrogen bond. This is another single bond, so we know it's a sigma bond. We know the hydrogen has a 1s orbital, and we know that this carbon here is sp2 hybridized, so that's going to be a sigma bond coming from the carbon sp2 to the hydrogen 1s. Right, so understanding the hybridization of the central atom is coming from its steric number is a very key component to this. And we'll do the nitrogen. Okay, so here, this nitrogen has a steric number of 3 also, so it's an sp2 nitrogen, right? And so this C double bond in is, it's a double bond, so we know it's a sigma and a pi. The sigma bond is coming from the carbon sp2 orbital to the nitrogen sp2 orbital. And the pi bond is coming from, well, again, we're going to arbitrarily pick which of the p orbitals are involved here. So we can say the carbon 2px to the nitrogen 2px. Okay. We haven't done any sp3s, so we'll do this next bond, and we won't do all of the rest of these, but you kind of get the idea, I hope, right? So we'll do that next bond, which is the carbon-nitrogen single bond. If it's a single bond, it's a sigma bond, okay? Now we need to know the hybridization. Well, that carbon is, if its steric number is 4, that is going to be an sp3 hybrid carbon. So this molecule, or this bond, is formed from you can do either the nitrogen or carbon first. We'll do the nitrogen first just to keep it in the order of how we're moving. So nitrogen, sp3, 2 orbital to the carbon sp3 orbital. Okay. Let's see. Yeah, so here, let's see. We'll do this oxygen carbon double bond to get us more double bond practice. So if we have this carbon oxygen double bond, we need to know the hybridization of each. The carbon has a steric number of 3, so it's sp2. The oxygen has a steric number of 3 because it's got these 2 lone pairs of electrons, so its steric number is 3, so it's sp2 as well. And so here you have a double bond, which means you have a sigma and a pi. The sigma will come from the carbon sp2 orbital overlapping with the oxygen sp2. And the pi will come from the pure p orbitals, carbon 2p, let's say y, to the oxygen 2py. Right? So what you're now able to do, hopefully based on this type of practice, is say, oh, if I pick out a bond, what are the orbitals that overlap to make that bond? Okay. Now, in each of these bonds, we're sharing a pair of electrons. That's something that comes about, based on some things that we'll look at a little bit later in the chapter when we start to put together a couple of different theories. We start to see what happens with bond energies and how bonds overlap and what happens to those energies. Okay. But that's the basic way of doing this and identifying the bonds in these different molecules. And again, it's a skill that's going to come in really handy for any of you who go on to organic chemistry, or for that matter, like biochemistry as well. That could be very useful in a biochemistry class. What happens is the types of reactions that can occur are going to have a lot to do with the orbitals that overlap in these molecules. All right, so that takes us sort of to the end of the use of hybridization for the moment. We'll come back to hybridization later on in the term. And basically tomorrow or on Monday, we'll come back to hybridization. Right now, we're going to introduce a new thing, okay? And the new thing that we're going to introduce is what's called molecular orbital theory, okay? So molecular orbital theory, and we're going to start out really simply, and we're going to keep it fairly simple as we put together molecules. So when we look at what we did before, with hybridization, orbital hybridization is a model that allows us to explain the shapes of molecules. But what orbital hybridization is not good at doing, it's not good at expressing what are called the electronic or magnetic properties of a compound. What it's really not good at doing is being able to say, hey, what color light will this substance absorb? Or if you remember line spectra, right? What color of light will it absorb or emit, right? It's not good at making that prediction. It's also not good at dealing with magnetic properties. Magnetic properties tell you whether a substance will be attracted to a magnetic field or not. And so what that comes about from is the number of unpaired electrons in the chemical structure, right? So if it has unpaired electrons, it will have magnetic properties. Okay, and we'll define that a little bit more later. But this other theory, that we're going to explore, called molecular orbital theory, will allow us to make predictions on the whether something is going to have magnetic or properties or not. And it will also give us some measure of understanding about which electronic transitions. When I say electronic transitions, just like when we talked the Bohr model, an electron going from a lower energy orbital to a higher energy orbital when it absorbs light, or going from a higher to a lower energy orbital when it emits light. That's what MO theory is much better at doing than the hybrid orbital theory, okay? Remember, these are just ways of modeling the molecules. Now, molecular orbital theory doesn't do as good of a job of modeling the shapes in a really tangible way, like we showed, how hybrid orbital theory is really good at helping us predict or explain, model the shapes of the molecules. Well, MO theory, not quite so much. And so here's the idea with MO theory. Okay, if you take, and we're going to start out with a very simple molecule, the hydrogen molecule. if you take a hydrogen, if you want to look at H2 from the standpoint of its bonding, well, we know that bonds forming is good, right? If you have two atoms that are separate, when those atoms come together and the orbitals overlap and they share electrons, that's going to be lower in energy than the separate atoms, okay? Those separate atoms aren't interacting with each other so much. When they come together, you get this orbital overlap, you have something that's more stable. And we know that it's more stable because we exist, right? If bonds were not more stable, all atoms would just stay as atoms, they would not form molecules. And so there's an inherent lowering of the energy when you have that bond that forms. So two atoms separately compared to the two atoms bonded. The two atoms bonded will be lower in energy. Now that happens when the overlap of orbitals occurs and those electrons are shared between the two nuclei essentially. And so over on the left, you see essentially what's an energy diagram where you have two hydrogen atoms. So one hydrogen atom initially here, and a second one that's far away. As those hydrogen atoms get moved in towards each other, the closer they go, right? In other words, when I move the right atom in closer to the left atom, there's a stabilization, there's an energy associated with this as the atoms get closer, at least to a point, right? As those atoms get closer, there's the stabilization, okay? At some point you reach the minimum, okay? That's the most stable point or most stable distance between the two nuclei. If you try to push them together, in terms of energies, you start to have that energy goes up very, very quickly because now you're trying to push the nuclei too close together. So you really want the nuclei apart enough to share the electrons very well, and form that bond. The bond is formed, and we think of a bond length as the length or the distance where we have that minimum energy down here, right? So whatever that distance is between the two atoms is going to be basically, in this case, where we have, it's like 74 picometers, okay? And that's going to be defining our bond length. And that's just sort of experimentally, you can model these things doing some calculations and find that minimum energy, and it agrees well with experiments. So this is for a hydrogen molecule. But when we say that we're pushing these hydrogen atoms together, what's going on with their orbitals, okay? And so when we do that, what we're doing is something similar to what we did with hybrid orbital theory to explain the shapes based on the central atom's orbitals. Only here, we're now going to take orbitals on different atoms and have those orbitals overlap. And when we have those orbitals overlap, we're going to combine their wave functions. When we combine those wave functions, and we're going to look at those wave functions as being coming from pure atomic orbitals for the very simple molecules that we're going to begin with, just to keep it simple. And we'll bring in hybrid orbital theory a little bit later to help us explain some other things. But when we bring those two atoms together, we're going to combine their wave functions. But again, like what we did with the hybrid orbital theory on that central atom, we have to combine the wave functions in such a way as to take into account all of these different possible combinations. So if we put two atomic orbitals in, we're going to get two molecular orbitals out. And the molecular orbitals are just what we're going to call them when these atomic orbitals combine, okay? So if I think about a hydrogen atom overlapping with another hydrogen atom, well, I've got, I can draw in my 1s orbitals, right? And if I move those together, something is going to happen to those orbitals. And that's really what's depicted over here on this side, okay? So what we can look at here is if we have those orbitals, when we move them together, we can add them or subtract them, okay? Is what we have here, okay? Another way of looking at this is I can add them in the same phase, which is what we have on the bottom there, right? Adding them together in the same phase, okay? Or I can look at it another way. I can say, oh, well, or I can add them together in opposite phases. So this would be more like adding together two things in opposite phases, okay? This is the way we can combine those two orbitals, the 1s orbitals from the hydrogen atoms that are forming the hydrogen molecule. If these orbitals, when they get pushed closer together, if they overlap and they're the same phase, we get constructive overlap in the middle, leading to a molecular orbital. that looks something like this. Okay, and so this orbital has symmetry that's along the bonding axis, right? If you think about this as being along the bonding axis, that means it's S or sigma orbital symmetry. It comes from the overlap of the 1s orbitals from the hydrogen. So this type of an orbital is labeled sigma 1s, okay? However, if we add them and they're in opposite phases, we get this other type of orbital where there's a node in the middle, right? And we can look at these as, right, so there's a node there, and you have orbitals, or this other orbital, there's a node in the middle, and these two lobes on either side of the node are opposite phases. Now that's going to be inherently less stable, right? Because you're canceling out that electron density, you're canceling out the wave function in the middle to describe where the electrons are. And so we're going to say that's a sigma still. It's still got symmetry on the bonding axis. It's still coming from the 1s orbital, but now we're going to give it this little star. And that star says that it's anti-bonding. Whereas if there's no star, right, it's going to be a bonding. In other words, when you have a bonding orbital, there's a stabilization that comes about from the adding two wave functions in the same phase. But if they're anti-bonding, there's going to be a net destabilization. Okay? And that net destabilization is occurring because they're out of phase with each other. And we have to take the orbitals together in both ways. We have to express them in both ways in order to do this modeling properly. Now, when we look at this from an energy standpoint, right, we can think about that over here from an energy standpoint, where you have the 1s orbital from the hydrogen, one of the hydrogen atoms, right? And that 1s orbital is going to have an electron in it. And then you have the 1s orbital from the second hydrogen atom. That'll have an electron in it. Now, when they combine, they give you a lower energy. If they combine in phase, they give you lower energy, right? So they're in phase, right? So there's your stabilization, right? So there's this stabilization here going to a lower energy. But we also take them into account with a destabilization. So you have this higher energy. So if they're out of phase. And what you have in the middle are the resulting molecular orbitals, right? So you can see that your sigma star 1s corresponds to the sigma star 1s there, right? And your sigma 1s corresponds to the sigma 1s here, right? So that on the top right is where you have the orbital pictures. This is showing the energy levels. Now, when you have this molecule, right, the molecule, right, this is an H2 molecule in the middle, right? Whereas on the either side, we had a hydrogen atom by itself, and on the other side, another hydrogen atom by itself. Well, when those molecules come and form a bond, the orbitals overlap. That's what gives you the difference in energy, the different height on this energy diagram. But you also have the sharing of the electrons. And so in the molecule, when you share the electrons, you fill orbitals from the bottom up like we did with electron configuration. So you're doing essentially an electron configuration for the molecule. And when you do that, you're taking the two electrons, one from either side, and you're putting them into the molecular orbital diagram. And so you have two electrons in the molecular orbital diagram. They're both going to be in the 1s orbital. And so what that leads to is the ability to do something which is predict a bond order, which is something we'll do next time. So right now we've started to construct these molecular orbitals in a somewhat different way than what we looked at with hybrid orbital theory. And this will lead us eventually to be able to explain the electronic and magnetic properties of molecules in a more sufficient way, okay? And so that's what we'll leave today's lecture with, and we'll pick that up tomorrow before our quiz. And tomorrow's quiz, remember, is Chapter 8 material. Yes, Jennifer.
Professor, I have a question about tomorrow's quiz.
Mhm.
And for the ESR